Thanks, Chris. Well, it's a great pleasure to be at the ICTS at 10 conference. I have had some association with ICTS for 10 years, not as long as David, but David did mention it to me, I think, in 2005, that Spenta Wadia is thinking about starting a new center, theoretical center well, the place was not known at that time because Spenta was going from one IAS officer to another IAS officer trying to secure land. But of course, I never dreamed that it will be such a beautiful place, such a thriving center. So I'm very happy to be here. This is my first trip. And thanks to David, Spenta, and now Rajesh, something very good is beginning. Well, it began 10 years ago, but it's taking shape and taking form. I look forward to coming back here over and over again. Okay. So I'm going to talk about some recent developments in condensed matter physics in which I have played a small role. But before I do that, I should mention, since mine is the first technical talk, that this is a rather difficult conference to prepare a talk for because the scope is very broad. And 5 different subjects, disciplines, in fact, are represented in ICTS, right? Condensed matter, particle and string theory, astrophysics and gravity just in physics, and then there is biology, computer science, math. And very little that we do touches up on all of those things. Very little, almost anybody does, touches up on all of those things. But fortunately, the topic I'll be talking about actually does, without exaggeration, combine 4 of the areas represented in ICTS. Computer science, and of course, condensed matter physics, math, and in fact, string theory. So biology and gravity, there is not much I can do. But of course, if a quantum computer is built by Microsoft, using the principles I'll be talking about, then maybe it will be used to solve problems in biology and gravity, because it will be a very powerful machine. So then it will connect all of those things. And this topic I'll talk about, it also have a very specific example of the interplay David alluded to, the interplay between experiment and theory, how and why, leading then to control and applications. I'll be talking about something very specific, although it connects with all those different things. And the specific thing really is built on interplay between experiment and theory, along with considerable help from math. So let me start by, so I'm going to try to combine these themes. So I'm going to start with computer science, because eventually I'll talk about condensed matter physics. And I'm going to start with a picture that I downloaded from YouTube. Now, if you do not know who this gentleman is, he actually went to school about 100 miles west of here in Bengaluru. That's Satya Nadella, who is the CEO of Microsoft. And what he's doing here, this is just downloaded from YouTube, completely public domain. This is 2 months old, and he's speaking to 4 individuals that I know very well. In fact, I have papers with 3 of these 4. This is Michael Friedman, who is a mathematician. He, in fact, proved Poincare conjecture on force sphere. This is Leo Konhaven, who is a condensed matter experimentalist. He's trying to find these Majorana particles that I'm talking about and then use them to build a topological quantum computer. Michael Friedman is the director of Microsoft Q, a Microsoft research station in Santa Barbara. Leo Konhaven is actually technically a Microsoft employee now, who is on leave to Delft University as a professor. He has been at Delft all his life, but became Microsoft employee a year ago. Charlie Marcus is a condensed matter experimentalist, professor at Copenhagen, also an employee at Microsoft. And this is Krista Savori, who is a computer scientist working on topological quantum computer. And they're actually discussing, it's a very instructive YouTube video. They're actually discussing these exotic particles that I'm talking about, how they'll be used to build a quantum computer, and presumably, since a very profitable company is involved, how these Majorana particles will lead to profit. As a Microsoft stockholder, I'll benefit from it. So this is a very long, distance coming from particles which are very exotic, as I'll explain to you, all the way to building an actual computer, which is a product. But this subject really encompasses all of that without any exaggerations. If I just told you that, you'd not believe me. So I put down, Satya Nadella's time is very, very valuable. He's sitting here discussing these particles with these scientists. And here he is in the same conference talking about the big things Microsoft will do. And you may not be able to read it. This is mixed reality, which I think is some version of virtual reality. I'm not sure. A more common terminology is virtual reality. This is AI, artificial intelligence. Everybody knows about it. Unless you have been asleep for the last 5 years, you hear buzz about it all the time. I don't quite know what it is, but it's big, in computer science, connected with words like machine learning, deep learning. I hear it all the time from my sons. And then over at the corner here is quantum computing. So this gentleman, CEO of Microsoft, who went to school 100 miles west of here, is talking about quantum computing in the same vein as these incredibly important concepts in computer science computing and in technology. So this is a subject that, no matter what else you think of it, it's certainly important in the common sense of the term. And what I'm going to convince you in the next 20 minutes is that it's also extremely fundamental. Well, there is an article in October 2016 in Nature News. This work, of course, has been going on for a while, where the scientific reporter said, inside Microsoft's quest for a topological quantum computer, why the company is hoping to build qubits out of particles that some scientists think might not even exist. Obviously, if they don't exist, it will not be a very good computer. Okay, that's science fiction. So these particles are so exotic that Nature put that in the headline. And so what I'm going to talk about is experiments that probably have detected these particles, or have they? That's where David's issue of experiment and theory, why and how, and the very high bar that we have in physics about discovery, particularly discovering something that's truly exotic and new. Bigger the claim, higher should be the bar. So that's what I'll talk about. So this particle that some scientists think, I don't know who these some are, but actually maybe one of them is me, it's possible, okay, is Majorana particle. So New York Times also chimed in, even before in 2014. They said Microsoft makes bet quantum computing is the next breakthrough. And I'm going anti-chronologically. This is 2014. And again, the theme is very similar. Explore an approach to quantum computing that is based on braiding of exotic particles. Braiding is the ordinary English sense. You take these particles and move them around each other, and something beautiful happens. And the thing that happens is something that actually conformal field theory tells us what happens. You braid and new things happen. And this proposed Microsoft computer, I took it just from this article, is mind-bending, very, very lofty word, even by the standards of the mostly hypothetical world of quantum computing, okay? And then they have pictures of three of us. This is Mike Friedman, Chetan Nayak, and me, because I think the picture is because we hold that patent to the topological qubit. So if a topological quantum computer is built, the elementary patent is what we wrote down a couple of years before that, 2013, I think. And what they say is that in the approach that Microsoft is pursuing, which is described as topological quantum computing, precisely controlling motions of pairs of subatomic particles, as they wind around one another, would manipulate entangled qubits. In fact, the gate operation, quantum gate operation here, is taking these Majorana particles and moving them around each other. And these particles are Majorana particles, okay? So far for the background. So the background is huge, that this thing may lead to an actual revolutionary product, which will be a new kind of quantum computer. So what is this Majorana? How can this thing do quantum computing? So to do quantum computing, you need a state, you need two quantum states. And these quantum states here are topological. So these are called Majorana qubit states. They're also known as Ising anyons because they obey the Ising anyon algebra. This is the Majorana zero mode. And basically what it is that it's not a free neutral Dirac fermion as in particle theory Majorana particle. I'm going to talk about that in a second. This is a Majorana that is localized at a defect. So it's a localized object, and it's a non-abelian Ising onion. This is not a free fermion. It's not even a fermion. It's an anyon. And what that object is, precisely this, that two of them together, so here is a Majorana, here is another Majorana, separated by some distance. This distance could be very, very large. Together, they encode one fermionic state. So you should think of them, two of them together, as somehow representing a fermion. And the two of them are very far. So in very loosely speaking, one can think of this as half a fermion. That's like a popular description, but technically it's not incorrect. So two of them together is a fermion. So now you know how it can be a qubit. Now, since in real world we only have fermions, you don't have half fermions, either these two states will be occupied together or they will be empty. That is your qubit. Your qubit is these two states occupied, so you have a fermion, or these two states are not occupied, in which case you have nothing. So these occupied or empty, this degenerate subspace, they have the same energy, is your computing space. Now, what happens, so if you now have, suppose instead of 2, you have 2 n-MZMs, where n is some large number, let's say n is 1,000,000. So now you have 2 million of these Majorana modes, then you can immediately see that the total size of the Hilbert space is going to be huge. It's going to be 2 to the power n minus 1. And this gives you the exponential power of quantum computing. That since it's non-locally encoding a fermion state, you have a huge ground state, and this ground state degeneracy is purely topological. It's not arising from any geometric symmetry that leading to some degeneracy. It's purely topological. And this non-local because you can see that 2 Majoranas could be very far separated. In reality, they may be separated by 10 microns. This non-local nature of the Majorana mode provides the power for doing this fault-tolerant quantum computing. And what it is, let me just not talk about that. What it is that it's basically a parity. As you see, all of this is happening in a superconductor. So talking about 1 fermion, 0 fermion, 2 fermions really not very meaningful, because in superconductor, because of Cooper pairs, you just talk about parity, and whether the fermion number is even or odd. What you have is a non-local parity. Either parity is going to be even or odd, that's your qubit, but the parity is non-local. Non-local means this thing is very well protected. Why is it well protected? Imagine you do something here, some perturbation here, change this thing. That's not going to do anything to your state, because your state is not just here. Your state is non-locally spread out between this and that site. This is where the protection comes from. This is what is known as topological protection, because this thing is provided by topology. So you can have phonons doing bad things here, phonons doing bad things there, impurities doing bad things here or there. That's not going to destroy this quantum state. So if you can create these particles and separate them, you have a very robust qubit. And this is where the topological protection is coming. And so you would not need any kind of error correction if you can create these particles, because there will be no errors. They are protected by their topological nature. So let me quickly go through why these are anyons. You may have heard that when you can only have fermions and bosons, 2 kinds of particles in nature, because a wave function is either symmetric, R1, R2 exchange gives you the same wave function, or the opposite wave function, very fundamental principle in quantum mechanics. And so exchanging twice should give you identity. So if exchanging twice gives you identity, psi square R1, R2 must be equal to psi square R2, R1, then these are the 2 possibilities. This seems to be, a fact, truth, as David said. But this turns out to be a dogma, because this is true only in 3 dimensions. Okay, this is true in 3 + 1 dimension, where you can have only bosons or variance, because when you go to 2 dimensions, things are much more interesting. In 3 dimensions, you cannot really have any non-trivial knots. You can just take it and slip it around, and it disappears. So if you have a fermion here, and you take another one around it, you can slip it, and it just vanishes, leaving nothing behind. But in 2 dimension, of course, you can have non-trivial knots. So it's known that 2D and 3D are very different, and this allows for richer statistics in 2 + 1 dimensions. 2 + 1 dimension, 2 exchanges. So this is time direction. You're taking this one, bringing it back, taking this one, bringing it back. So you got back where you started, but you created 2 knots. And these knots are there in time. So 2 exchanges are not identity, because these knots exist. So in 3 + 1 dimensions, you can undo these knots, but in not 2 dimension. So in 3 + 1 dimensions, 2 exchanges always give you identity, because there are no knots in the world line. But in 2 + 1 dimension, 2 exchanges do not need to give you identity. And there is the difference between break group and permutation group. And this is at the heart of this topological quantum computation. So this then immediately led to the idea that in low dimensions, 2 dimensions, you can have objects called anyons, where the statistics is neither fermionic nor bosonic. It's something intermediate. And they're called anyons. And then something even more interesting could happen. Suppose such changes in the statistics are non-abelian. Suppose you started the degenerate ground state, then when you take them around, you could switch the wave function. And if you switch the wave function, then there'll be unitary matrix representing this Bray operation. So those matrices could be non-abelian, and so the matrix representation of the Bray group may be non-abelian. When that happens, then you have this strange particle, these Majorana particles. The particles we are talking about will obey these statistics. Of course, what I just told you is that what is allowed. What is allowed by nature does not always happen. Okay? So nature allows there to be objects, particles, which are more complicated than fermions and bosons in 2 dimensions. But that does not mean in 2 dimensions those objects must exist. Maybe only fermions and bosons exist. Maybe these things don't exist. So experiment will have to tell us whether these objects exist or not. Okay? So if such 2D non-abelian states exist in nature, this is a very big if, as David Gross emphasized, experiment will have to tell us that. Theory can only present the possibilities, and then experiment tells us if that happens or not. Then topological quantum computation may be carried out by adiabatically rotating the states within this degenerate manifold. Majorana is such an alien. Now, where do you look for Majoranas? Okay, these Majorana modes. So let me just quickly tell you about Ettore Majorana, who mysteriously disappeared at age 35 in 1936 or 37. So he actually was interested in understanding neutrons, and then it turned out the theory of neutrinos, that we know that solutions of Dirac equations are complex, but a very simple modification produces real solutions. And of course, if it's real, then they cannot be charged fermions. So Majorana fermion in particle physics are objects which are fermions. They're solutions of Dirac equation, but they're neutral solutions of Dirac equations. Okay? And so then, since they're neutral, the particle, and the way they are, not all neutral particles, they have to be neutral, but that's not enough. They will be their own antiparticle since they're completely real. So gamma, which creates a Majorana particle, is equal to gamma dagger, identically equal. So Majorana fermion is its own antiparticle, which in fermions you don't have examples of that. In bosons, that's trivial. So in particle physics, neutrinos may be Majorana fermions. This question is still an important open question. Lots of experiments are going on to see whether neutrinos are or are not Majorana fermion. But what we are talking about is something more complicated. We are talking about realization of this property itself. Okay? I mean, in some sense, Majorana is a slight misnomer in our case, but this name has stuck. So we will have an object where gamma is equal to gamma dagger. It's some kind of emergent Majorana. The possibility that the Majorana operator itself could be realized in low-dimensional condensed matter systems. Okay? So the question now is that how do you do that? How do you create an operator like this intrinsically in solid state system? It turns out it's very simple. Because superconductors allow you to do that in a seamless manner. As you know, the ground state of superconductor is filled with Cooper pairs. So Cooper pairs are not excitation, they're ground state. But Cooper pairs, if you create excitations which are Bogoliubov particles, they are mixtures of particles and holes. Now, this mixture, if you now make U is equal to V star, you immediately have this property, gamma plus is equal to gamma dagger. So all you need to do is to go to the gap of a superconductor and find an object where U is equal to V star. So that means that object will be exactly at 0 energy. So all you have to do is find a state at the gap, exactly at the mid gap of a superconductor. Once you have that object has to be, that bound set has to be a Majorana particle. So that sounds very easy until you realize that fermion doubling doesn't allow that. If you have ordinary spinless, ordinary spinful superconductor like SOF superconductor, you'll never have a 0 energy state because there is an exact symmetry, particle-hole symmetry that will avoid that. So it was clear what you need, the most simple thing you need is some kind of spinless POF superconductor. So the question now boils down to, can we find spinless POF superconductor in nature? It turns out spinless POF superconductors do not exist in nature. Well, then we'll engineer them. This was the idea we had. We said, well, if they don't exist, you can engineer them. So it turns out that if you take an ordinary superconductor, couple it to the semiconductor, which has spin orbit coupling, and then somehow create a spin splitting in the semiconductor, then you effectively have induced a spinless POF superconductor in the semiconductor. So it's proximity-induced superconductivity. So it's a complicated multi-layer system where the superconductor induces superconductivity, and then the spin orbit coupling and spin splitting together creates a condition when the spin splitting is large enough that this system behaves as a spinless POF superconductor. And for technical reason, it turns out it's much easier to do this. So you're breaking both time reversal and spin rotation symmetry to create spinless POF superconductor. And once you have done that, then you'll immediately have, theory says, then you'll immediately have a state at zero energy, and that state will be Majorana. You don't have to do anything else. Just create this system, that's it. That's what it predicted. It turns out for technical reasons, it's easier to work with one-dimensional system because you don't want to avoid orbital effect of a magnetic field. So if you go to a one-dimensional system, we predicted that indium arsenide and antimonide, put it in contact with a superconductor, apply a magnetic field, and if you do that, then theory immediately predicted that you will have a Majorana mode at zero energy. So let me show you a numerical calculation. That theory, I don't have time to go through it. Let me skip this, I already explained this. So this is just a numerical calculation. We created that system in the computer, indium antimonide nanowire with a magnetic field applied with a superconductor nearby. When the magnetic field is small, this is the spin splitting. When the spin splitting is small, you just have a gap. This is just the regular superconducting gap. There is nothing in it. When spin splitting is large compared with the gap of the superconductor, this is chemical potential. When the spin splitting is large, this is just direct numerical calculation. Immediately you find that you have zero energy state, and then wire goes like this. This is the length of the wire. You have zero energy state, bound state. These states are Majorana states. And if these states are seen in the lab, you can immediately build a topological quantum computer. Of course, this is all theory. This theory was very exciting, and there was a lot of activity because it's a very simple system. I mean, literally very simple system. Hundreds, if not thousands of groups can make these systems in the laboratory. I'm not going to talk about that. This is, since it's a high-power theory, I thought that I should show some equations. Basically, one question that comes up is that, okay, you have this system, but is it stable to disorder interactions? So we did some complicated RG plus replica theory showing that it's stable. The fixed point is stable, but it's not particularly important. So then you even said what kind of experiment one has to do. Take a nanowire, so this is from the theory paper, take a nanowire, put it on a superconductor, apply a magnetic field, then by some kind of tunneling measurement, look for this particle. And we said what you'd see, since there is zero energy state, you'll see a peak at zero voltage. You'll see a large peak at zero voltage, okay? So this was theory. But within a year, Leo Konhaven did an experiment, created a system very much like what you're saying. Here is the nanowire. Here is the superconductor. In his case, it was niobium. Nanowire is indium antimonide. This is just a contact, gold contact to measure the current through here. And he saw this zero bias peak. This is the peak at zero voltage. So, and here's the theoretical numerical work. And you can see that the zero bias peak, which is associated with the Majorana modes being localized here. So this created tremendous excitement right away. 6 different groups immediately reproduced these results. So a lot of excitement happened. And I'm showing you some very recent results from Charlie Marcus's group, where you can see this is, again, a color plot, which is not easy to understand what's going on. Here is the superconducting gap. Here is a zero energy state. Beautiful zero energy state, which is stable in magnetic field. And everything looks like it's going very well. And here is a zero energy peak. Beautiful zero energy peak, just about from a year ago. Beautiful zero energy peak. But this is the system Charlie Marcus was looking at. But the problem we found, and I would not be able to get into the depth of it, time is running out, is that when you try to simulate this system that Charlie Marcus was doing in the lab, we said, well, let's study this system theoretically, this precise system theoretically. And we did that, and we found results which are almost identical to what Charlie was getting in the lab. You see, this is, you can't even tell which one is the experiment, which one is theory. This is theory, this is experiment. You see, experiment, they see a zero energy, we see a zero energy peak. Experimentally, they see a gap closing, we see a gap closing. Experiment theory look very similar, very, very similar. So it's wonderful, everything works. Only problem is that these modes that we found are not Majorana modes at all. These are trivial, non-topological states who just happen to be very low energy. Problem is experiment, this zero is not a set of measure zero. This zero, experiment zero has meaning zero is what? Zero is 5 microvolt, 10 microvolt, 0.5 microvolt, nanovolt. There is always a number. Experimentally, nothing is precisely zero. So if you see this line experimentally, it's not zero. This is not exactly at zero. So this thing is not exactly at zero. But we found a lots of states because of the symmetry of this problem, lots of low energy states accumulate near this zero line. And it was devastating that you could have these Andree bound states, which are very low energy states. So what experimentally seeing may be Majorana, but may not be Majorana. Okay, so we cannot be sure. And the situation is improved slightly. This is our theory paper, which is very unfortunate, but that's what nature is telling us. Nature is telling us in these systems, yes, you'll have strictly zero energy Majorana state, but you'll also have states which are very close to zero energy, which are not Majorana. And this is a very big problem. Experimentally, you do not know. You just see a zero bias peak. So recently, one thing would be that if you see the quantization associated with the Majorana, this is like quantum Hall effect quantization, then maybe one has slightly more faith. I did not emphasize. None of these zeros that Charlie Marcus saw are quantized. You can look at the value. I should have emphasized that. Sorry about that. If this value is 0.1, this number should be more like 2. So this is like factor of 20 lower than the quantized Majorana value associated with the theory. So very recently, I worked closely with Leo Cohnhaven's group, and I cannot go into the details because there is no time, but through just sheer material science, spending a huge amount of money, which we had, because this is an important technological project now, and we did see quantized Majorana conductance. Here is experiment. As you can see, it's quantized at 2 square over h as theory predicts, and this is our theoretical simulation of the experiment. Realistic simulation shows pretty much the same. So it looks like we may have Majorana quantization, which means we may have Majorana, but it's not 100% guaranteed that it is. The situation is better, but the only way to know for sure is to do braiding and see the non-local topological property. You have to actually show that this thing is a true anion in the sense, non-abelian anion. Short of that, I do not see how you would know, because both have zero bias peak, and that's what the subject is right now. So these particles are very exotic, and these particles are extremely exciting and may have enormous application. As David said, that once you have theory and experiment going together, if you can control it, it could lead to application. So I'll just conclude with this slide that the subject began. In the beginning, it was all theory, like often happens in physics. Standard model, asymptotic freedom was a theory, Higgs was a theory, gravity wave was a theory. So here it was all theory for the first 10 years, very exotic theory with topological quantum field theory and condensed matter physics and quantum computation coming together. In the middle, last 5 years, the excitement increased because experiments started seeing some of the features theory predicted. But then there's a setback. It turns out some of the non-topological objects could have very similar behavior also. So now the question is that are we at the end? Is it the beginning of the end or end of the beginning? We do not know. But in some sense, the end is the real beginning. With the really exciting stuff, all the topological properties in the future, you have to do the braiding and show that the system is really behaving like these exotic particles, and that has not happened yet. That's where we are. Once that happens, then building the quantum computer, as physicists would say, is just engineering. Will then that move away and leave all the hard work for the engineers. But that has not happened yet, so we are at a very exciting time. I'm hoping this will happen soon, but I do not know, because it has to happen in a lab, not in a notebook with a pencil. Thank you very much.
Questions? Anybody? Comments?
In your simulation of one-dimensional wire you have shown, the zero state is formed only at the end of the two ends. Why is that?
These are, for a number of reasons. Yeah. First, that's what they form. Okay, this is just a fact. When you do the theory, solve the theory. Now, when I say end, of course, maybe that's what I'm alluding to. They have a localization length. This is a real bound state. So its end may not be end. If that localization length is large, then of course the end could be throughout the whole system. So now you are bringing up a question that I did not discuss, that unless the wire is very long, there is no difference between end and the bulk. So if the wire is short, meaning the length of the wire is comparable to the size of this Majorana wave function, this Majorana wave function is just the coherence length of the superconductor. So coherence length goes as the inverse of the gap. So the size of this, how close it is to the end, depends on how large the gap is. If the gap is infinite, then it's a delta function at the end. For any finite gap, it spreads over some region. If that region covers the whole length of the wire, then this object is not non-local anymore. Then the two Majoranas overlap. When the two Majoranas overlap, you cannot do topological quantum computation either, because then those are not topological objects. So one has to be careful about that also. So what you're asking is very important. How far, in the end, it is a very important question, and I don't have time to discuss that. But this has been looked into great depth, and experimentalists have to worry about it. And this is connected to the splitting of the Majorana, because when they overlap, the Majorana is no longer at zero energy. It creates symmetric and antisymmetric states, and it becomes a bit finite. Okay.
Yeah. I have a question here.
Oh, yes.
Yeah. So, just a question on the quantization of conductance at zero bias.
Yes, please.
I understand the Majoranas will give you 2 square by h.
Yeah.
But if you have large number of zero energy states because of other sources,
yeah.
at the unitary limit, even they would give 2 square by h.
This is in fact our paper. This is our 30-page paper that I told you. This is the monkey wrench that I threw into my own patent. It shows that you will generically get 2 square over h also. Actually, generically, you get 4 square over h. Right. Because you think of that Andree bound states as 2 Majoranas, each contribute 2 square over h. So generically, you get 4 square. But because of the question this gentleman asked, what happens is that you have now 2 Majorana. One of them is always close up to the edge by definition. Right. And the tunneling probe just couples to that. So you just see 2 square over h. You don't see 4 square over h. Okay. We showed that in extensive details, precisely the problem you are bringing up, that even seeing quantization does not prove topology. Yeah. Okay? Because of this problem. Yeah. This is the farthest you can go using tunneling conductance measurement. Now, what I would say is that suppose they have 1,000 words, and in every word, the moment they do experiment, they see 2 square over h. I would then believe it's Majorana, because there is no fine-tuning then. To get the Andree bound set all to give you that, you need a lot of fine-tuning. And it has to be a very strange situation. So if thousands of words show 2 square over h, I'm sold, Majorana has been seen. But this one was 2 words, and the theorists and experiments have worked closely together for 8 months to do that. So the question still remains. Okay, did I answer your question? That's what you're asking.